Titan. If you could travel at the speed of light, you'd pass Mars about 4 minutes into the voyage. At the 30-minute mark or so, you would pass the giant ball of gases known as Jupiter. Then, some 70 minutes after departure, you would finally arrive at Saturn surrounded by those beautiful rings. Like Jupiter, Saturn is a large, gaseous planet. Finally, you'd reach Titan. With a diameter of 5,000 kilometers, Titan is about 3/4 the size of Mars. It's a moon the size of a planet. Fully cloaked in that orange haze, Titan's true appearance was not known until the 21st century. (1997) saw the launch of the Cassini-Huygens mission. The Cassini orbiter, equipped with cameras and other instruments, and carrying the Huygens probe, was sent to investigate Saturn and its moons, especially Titan. In 2004, 7 years after liftoff, Cassini-Huygens reached the vicinity of Saturn, 1.4 billion kilometers from the Sun. Cassini then proceeded to enter into orbit around the planet and its satellites, and to commence scientific observations. It took this image of Titan. For the first time, Titan's true features began to show from under that thick haze. The day was approaching when we would finally be able to see the surface of Saturn's giant moon. In December 2004, the Huygens probe separated from Cassini and coasted to Titan. The target landing site was near Titan's equator. What that site would be like, no one knew. Titan's atmosphere is 1,000 kilometers thick. The probe entered it. Huygens deployed a parachute and drifted down, jettisoning its heat shield. This image, taken from a height of 152 kilometers, was Huygens' first view of Titan, which was still obstructed by haze. Huygens was shooting still images as it descended. Its microphone also captured the sound of the wind rushing by. This was the first sound recording ever made of an alien environment. These images of Titan's surface were taken by Huygens from 16,000 kilometers up. Black veins, like the branchings of a river, are visible. It does look as though they are flowing to the mouth of a river. Now, from 8,000 meters above Titan, it looks just like the sort of coastline we're used to seeing on Earth. Finally, the landing. This is an image taken by Huygens just after landing. What look like rocks and pebbles strewn about over a flat plain are actually chunks of ice. The surface temperature is minus 180 degrees Celsius. Atmospheric pressure is a little higher than Earth's, 1.5 bars. The horizon seems blurred by mist. This is exactly like some rocky desert landscape on Earth. High above, The Cassini orbiter continued its observations. In the equatorial region where the Huygens probe landed, Cassini discovered a strange pattern. Some sort of regular striping. Further observations found similar striations covering some 20% of Titan's surface. Ralph Lorenz has dedicated himself to investigating this strange striped pattern. He is trying to solve the mystery of Titan's stripes by comparing them to patterns he finds on Earth. This is the Mojave Desert in the western United States. Lorenz believes Titan's stripes are like the peaks and troughs of desert sand dunes. There are indeed real similarities.
It's remarkable somehow that despite the different gravity, the thicker atmosphere, and the different material that the sand is made of, somehow the landscape ends up looking almost exactly the same as many places on Earth. By comparing the shape of the dune and the interaction with the rest of the environment, we can get an understanding of how these structures formed. And for example, different shapes of dunes form in different wind patterns.
So the goal is to solve the mystery of Titan's stripes by investigating terrestrial desert dunes. Lorenz's first step is to send up a kite with a camera for an aerial overview. He's looking for a place that has a striped pattern like Titan's. Next, he mounts a dune buggy equipped with GPS. He wants to measure the heights of dunes and the angles of their slopes. The shapes of sand dunes change by the minute. Lorenz plants a stake with a streamer attached. In fact, he plants a whole line of them along this slope. This will show what sort of wind creates this type of dune. The wind is blowing from screen left, across a gentle slope. Then it swirls around, as if to carve out that slope to the right. So it's become clear that here the wind flows from the milder slope over and down the sharper slope. Lorenz believes that the stripes on Titan are also wind-sculpted sand dunes. A closer look at that image of Titan's stripes shows ridges with milder and sharper slopes, similar to those in the Mojave Desert. So Lorenz conjectures that the wind on Titan must have been blowing from left to right. The winds blowing on Titan's dunes, however, are thought to be weaker than the winds on Earth. The reason for that is that Titan's gravitational force is only 1/7 of Earth's. A relatively small action can produce a big result. So on Titan, effects similar to those seen on Earth are being produced by mild winds.
Titan is still an active world where, geologically speaking, processes are still happening. And the fact that we can see sand dunes, for example, suggests that the winds that move the sand around are still active, that we're seeing a dynamic planet, much like the Earth.
There was another unexpected aspect to those images taken by Huygens. Look closely at those chunks of ice on the ground. They are reminiscent of stones turned over and over by rivers on Earth. Sharp edges are worn down. They're rounded, like pebbles. So there may well be liquid on Titan. This discovery attracted attention and astonishment. Meanwhile, the Cassini orbiter made a surprising discovery of its own. Black spots and blotches were visible near Titan's north pole. Radar observations showed them to be lakes filled with some liquid. They number in the hundreds, and some of them are huge. This is the first time liquid has been found on the surface of any celestial body other than Earth. The lakes are dotted with islands and fed by rivers. But with a surface temperature of minus 180 degrees, any water on Titan would have frozen. What liquid could it be in these lakes and rivers? This is it. Liquid methane. On Earth, it's normally a vapor, but at extremely low temperatures, it condenses into a liquid. Methane melts at minus 182 degrees Celsius. It boils at minus 161 degrees. In the 20-degree range between those two extremes, it exists in a liquid state. The temperatures on Titan's surface are just right for liquid methane. Methane is composed of one carbon atom and 4 hydrogen atoms. It's the simplest hydrocarbon, and it constitutes the bulk of the liquid in Titan's lakes. A portion of the liquid is ethane, another hydrocarbon with similar characteristics. Scientists at the Jet Propulsion Laboratory are trying to determine how Titan's methane lakes were created by conducting experiments here on Earth. Christophe Sautan is an expert on bodies of ice found in the solar system. This device is called the Titan chamber. With internal air pressure at 1.5 bars and a temperature of minus 180 degrees Celsius, it reproduces Titan's environmental conditions. Inside is placed a disk of ice, standing in for the terrain on Titan. They then release droplets of liquid methane onto the surface of the ice. The methane disappears immediately, absorbed by the ice, like water being swallowed up by a thirsty Earth.
So the big surprise, something we did not expect, is that when the methane falls on the ice, well, actually the methane got sucked into the ice. It gets absorbed. It doesn't run on the ice.
However, if methane continues to drip onto the ice, eventually it begins to pool on the surface. This suggests that wherever there are lakes on Titan, the surrounding ice must be saturated with methane. During its landing on Titan, Huygens measured the concentration of methane. That concentration gradually rose the closer the probe got to the surface. Then, the moment it landed, there was a sharp increase. It is thought that this was due to the heat from Huygens vaporizing the methane that permeates the ice. On Titan, liquid methane acts in ways similar to water on Earth. In June 2012, for example, Cassini observed a strange phenomenon near Titan's south pole. An oddly shaped mass seemed to be squirming about in the atmosphere. It was a cloud, swirling. a cloud made up of methane. On Earth, water is recycled as water vapor and rain. One of the factors prompting this is seasonal change. On Titan, the same sort of mechanism seems to be at work. Titan is tilted on its axis, some 26 degrees off vertical. The Earth has a 23.4 degree tilt. It's another point of similarity. Along with its parent planet, Saturn, not shown here, Titan takes 30 Earth years to orbit the Sun. The tilt of its axis gives birth to different seasons. At this location, Titan's northern hemisphere experiences the long days of summer. The northern hemisphere is warmed, producing rising atmospheric currents. Liquid methane on Titan's surface evaporates and is carried southward. Near the South Pole, it is winter. The methane gas is cooled, condensing into a liquid or even solid state. It can form clouds. Like that huge swirling cloud Cassini spotted. When it's winter in the northern hemisphere, the cycle reverses. Now the methane cloud forms near the North Pole. Underneath that cloud, methane rain begins to fall. Since methane is more viscous than water, its raindrops are larger, with diameters of about a centimeter. But as Titan's gravity is weaker than Earth's, the droplets fall more slowly, about 1 meter per second, like a soft snow on Earth. They soak the icy ground on Titan and form lakes. Wind blows, rain falls. When people could finally see Titan close up, they were astonished at how much it resembles Earth. In 2007, the Cassini orbiter spotted something truly peculiar on Titan's surface. A land formation, some 70 kilometers across, in the shape of a flower. What could it be? Perspective can be gained by combining images taken from two different points of view. A three-dimensional image of the topography emerges. That strange formation turns out to be a rugged mountain, featuring a 1,500-meter high peak. There's also a chasm that looks like it might be a volcanic crater. From that, one can infer a formerly active volcano. That volcano has been an object of particular interest to Jonathan Lunine, an expert on Titan's internal structure. He says that the volcano did not spew lava. Rather, it pumped up a mixture of ammonia and water.
One thing to remember is that when water is mixed with ammonia, it can stay liquid down to very low temperatures, down in fact to minus 100 Celsius. But at that point, within a few degrees of that point, the liquid is actually very viscous. It's almost like basalt. And so if that is what is flowing out on the surface, we would see very thick flows.
Lunine believes that under the ice beneath the volcano, there's an ocean. He came to this conclusion due to changes in Titan's shape. Titan completes its elliptical orbit around Saturn once every 16 days. During that time, it regularly feels the changing effect of Saturn's gravity. In short, it experiences tidal forces. At its farthest point from Saturn, Titan is almost perfectly spherical. But at its closest point, where Saturn's gravitational pull is the strongest, Titan grows fatter. Its diameter alters by as much as 10 meters. Lunine says that Titan can transform so dramatically because internally it is not made entirely of solid rock. Lunine's observations suggest the following picture of Titan's structure. The outer crust of ice is some 50 to 100 kilometers thick. The center is comprised of two types of bedrock. In between the ice and the rock, however, is a layer of liquid water. The bedrock generates heat, says Lunine, permitting the water to remain in a liquid state. This ocean layer is some 300 kilometers deep. Ammonia, present in Titan since its origin, has also dissolved into the water. It is thanks to this ocean layer that Titan can change shape so flexibly.
The interior is warm enough that really only liquid water is a suitable, stable material in that region. So we're pretty sure from the gravity experiment that Titan has a liquid water layer under its surface.
According to Lunine, the tidal forces caused by Saturn in turn stimulate volcanic activity. Tidal forces cause friction along the boundary between the ice and the subsurface ocean. The water heated in this way melts some of the icy crust. It builds up like terrestrial magma and eventually forces its way up above the surface. This ammonia-laden water flows out from Titan's volcanoes like lava. Lunine believes such volcanoes are proof of an underground ocean. Beneath Titan's icy shell, a whole new world lies hidden. Saturn has over 60 moons. Among them are Enceladus, ice-covered like Titan, and Hyperion, pockmarked with craters. Mimas has this huge crater. Those are just a few of Saturn's moons, but they all have practically no atmosphere. Only Titan boasts an atmosphere that extends as far as 1,000 kilometers into space. Actual measurements reveal that this atmosphere is 98% nitrogen. The rest is largely methane. Why is Titan the only one of Saturn's moons with a thick atmosphere? Solving that mystery through experimentation on Earth has been a preoccupation of Yasuhito Sekine. Sekine believes that Titan's atmosphere was generated by an extraordinary mechanism. The mechanism? Collisions with small celestial objects. Sekine is trying to reproduce that effect using a laser. When Titan was first formed, its icy landmass contained about 1% ammonia. So inside a vacuum chamber, a disk of ammonia water ice stands in for the young Titan. The laser beam enters from the left of your screen. It strikes a projectile, which then impacts the ammonia disk. That was the laser shot. Gases released by the impact are measured. One is nitrogen, released by the disintegration of the ammonia. Titan's thick atmosphere contains large amounts of nitrogen. According to Sekine's calculations, based on his experiments, repeated impacts by small celestial objects could have produced just such an atmosphere.
タイタンの地殻中にもともと入っているぐらいのアンモニアの量があれば今の1.5気圧の窒素の大気を作ることができるということを明らかにしました。 重要な点はですね、大きい天体でないと大気を重力的に持てないということです。なので他の衛星たちは同じように衝突は起きたんですけど、それぞれが小さいがために窒素の大気を持つことができなかったと。
For example, Enceladus, one of Saturn's other moons, is merely 500 kilometers across. That is 1/10 of Titan's diameter. Saturn's other satellites are also small, with weak gravitational fields. So even if they've been similarly impacted, they haven't been able to hold on to any atmosphere. But did Titan in fact experience repeated bombardment by small celestial objects? Hal Levison uses computers to calculate the history of the solar system. He has advanced the revolutionary theory that some 4 billion years ago, the entire solar system was shaken by a massive event. Levison argues that when the solar system was forming 4.6 billion years ago, Uranus and Neptune were closer to the Sun than they are now. He inputs the location and size of the planets, and also of the small celestial objects that lie further out. Then the simulation begins. At first, the basic situation did not change much. But some 600 million years later, Uranus and Neptune were suddenly flung to the outer realms of the solar system.
Then out. Okay? And that caused the giant planets to slowly spread. It was infinitesimal. You wouldn't have noticed it, but the orbits were slowly changing. And that continued until Jupiter and Saturn got to the point where Jupiter was going around the Sun exactly twice. Every time Saturn went around once, and that configuration is what set the whole instability off. Okay, so you went almost overnight from a time when, okay, there was a little bit going on, but not much, to this very violent period where all hell breaks loose.
The smaller celestial objects, shown here in green, had formed a ring at the outer edge of the solar system. But then the gravitational force of Uranus and Neptune violently scattered these objects. The result was that in the period from 4 billion to 3.9 billion years ago, the planets of the solar system encountered a barrage of small celestial objects. During this period, Titan also was hit repeatedly, developing a nitrogen-rich atmosphere. That made it a very special moon.
たった1億年とかそれぐらいの短い期間なんですけど、その間にですね、その 1.5 気圧という膨大な量の大気を作ることができたというふうに考えられます。タイタンというのはですね、唯一人類が初めて見つけた生きている天体だというふうに言えると思います。で、地球と同じようにですね、表面で液体が存在して、それが蒸発して雲を作って雨を降らしてというような循環が起きているのはですね、現在の太陽系の中では地球とタイタンだけです。で、その点において40億年前のその出来事というのはタイタンにまさに命を吹き込んだと、生きている天体にしたという意味で非常に画期的な出来事であったというふうに思っています。
1977 saw the launch of Voyager 1. Its mission? To explore and observe the outer planets, from Jupiter to Neptune. This was its view of Titan. It was a close look, but still the moon was shrouded in a thick orange haze. However, even then, one scientist maintained that the haze held the secret to sparking life below. Bishun Kare has been trying to penetrate the mystery of Titan's haze since the early 1970s. He participated in the Voyager mission. He is focused on the haze as being itself a source of life. Kare introduces a nitrogen-methane mix into a sealed flask to simulate Titan's atmosphere. The flask is fitted with electrodes. Now Kare discharges them. This is meant to reproduce the effect of lightning or other energy surges on Titan's atmosphere. It's about 10 hours since the start of the experiment. A reddish-brown substance has become visible inside the flask. Carré claims that this is the very same substance as the haze enveloping Titan. So what happened inside that glass vessel? First off, the electrical surges split apart the molecules of nitrogen and the methane. Their atoms recombine with carbon and other atoms in all sorts of ways, forming a variety of new organic compounds. Analysis showed that some 200 types of organic compounds had been created in this experiment. Organic compounds are the materials out of which our own bodies are made. They are the building blocks of life. It was thanks to Carré's work that Titan came to be considered one of the celestial objects on which life might exist. The Cassini orbiter's close-up observations of Titan have come some 30 years after Carré's experiments. Will they confirm that Titan's hazy atmosphere has in fact given rise to organics? The INMS is a device that measures molecular mass. Cassini has used it to determine the composition of Titan's atmosphere. Cassini's data were streamed back to Earth, where they were analyzed by Hunter Waite and his colleagues. Waite led the team that designed the INMS instrument package carried aboard Cassini. Waite's lab was able to reproduce and confirm Cassini's data by utilizing the same INMS system. They could then analyze accurately whatever molecules or compounds the instrument had detected. The results were astonishing. Rendered in the form of a chart, each of the different molecules identified by Cassini is represented by its own colored area. Various organic substances were created in Titan's atmosphere, ranging from ones with a single carbon atom to more complex ones with 6 or 7 carbon atoms.
When Cassini sent back data, we found out that the upper atmosphere was much more relevant than we ever thought, that most of the chemistry seemed to be going on in the upper atmosphere, that very large molecules were being created in the upper atmosphere, way beyond our expectations. Titan is one of the best organic factories in the solar system.
Bathed in ultraviolet and cosmic rays, Titan's upper atmosphere is continually engaged in converting nitrogen and methane into a rich array of organic compounds. As these compounds collect in the lower atmosphere, they produce Titan's famous orange haze. Finally, they are precipitated with methane rain onto the surface as well. It's been 4 billion years since Titan's atmosphere was formed. During that time, it is estimated the organics settling onto the surface have created a layer dozens of meters thick. The dunes discovered near Titan's equator are thought to be a large deposit of these organics.
Now on Titan, the sand is made, we think, from organic material, and we think that material comes down and gets built up into sand-sized particles that are then accumulated by the wind to form dunes much like these.
Amidst this accumulation of organics on Titan's surface are substances of vital importance to the emergence of life. That finding was made by a young researcher with a specialty in organic chemistry, Sarah Hurst. Hurst has undertaken a minute examination of the organic compounds discovered in Titan's atmosphere. She's written her own computer program to do that. Based on Cassini's observational data, she faithfully simulates the composition of Titan's atmosphere and produces the same organics. Next, she uses her computer program to determine the molecular structure of every compound.
These peaks right here are the masses of the ions in the mass spectrum data, and then it's the number of carbon, nitrogen, oxygen, and hydrogen in each of those peaks. And so then what the code does is it goes through and compares this information to a list that I've given it of all of the amino acids and nucleobases that we're looking at. So here we have, at 136, we have the molecular formula of adenine, which is 5 carbons, that matches. It has 5 nitrogens, it matches. No oxygen, and then 5 hydrogens. So we know from this that we have the molecular formula of adenine in this sample.
Genetic information for all life on Earth is encoded in DNA. Adenine is one of its 4 major components, or nucleobases, and all 4 have been produced in Hurst's experiments. If these nucleobases combine in such a way that they create DNA, then a huge step forward will have been taken towards life itself. With this discovery, speculation mounted that Titan might actually be capable of harboring life. Life on Titan? It may in fact already exist. If it does, what would it look like? The search is on for the answer. Trinidad and Tobago form an island country in the southern Caribbean. They have a population of about 1.3 million. They also have one of the most unusual lakes in the world. It's called Pitch Lake. It contains not water, but naturally occurring asphalt. It bubbles up from an oil field that lies underneath, creating a lake of asphalt that's 40 hectares in area and 80 meters deep. Strangely enough, Pitch Lake is the site of fieldwork being done by astrobiologist Dirk Schultz-McCook. He thinks that Titan is the best candidate for the location of extraterrestrial life. He's come here to try to envision what life forms on Titan might be like. Asphalt, like methane, is a hydrocarbon comprised entirely of carbon and hydrogen. You wouldn't think this was a substance that harbors life, but Schultz-McCook says it actually does contain microorganisms.
Well, this is one of the few environments where it's similar to Saturn's moon Titan, where we know that we have hydrocarbon lakes on the surface. Obviously, Titan is very cold, so it's still different than from over here. But we do have the liquid methane and ethane, which are also hydrocarbons. And if we can find out what kind of organisms are living here in the asphalt lake and how they adapt to living in the hydrocarbons, we think we can get some ideas to how life could operate on a moon like Titan.
Asphalt contains almost no water.
Did you say that there's microbes in it?
Yes, there's microbial organisms in that liquid asphalt.
In this thing?
In this thing, yeah.
Like maybe 1, 2
Millions.
millions.
Yeah.
Genetic analysis identified some 600 new types of microorganisms living in the asphalt. Most are archaebacteria, related to the primordial microorganisms that live in extreme environments.
So for them, actually, it's a great environment, it's a great food source, and basically a never running out food source because it's getting supplied from deep down there.
On Earth, there are microorganisms that can use asphalt for sustenance instead of water. Schultz-McCook is convinced that in Titan's lakes, there must be life forms that exploit methane in a similar way. Another scientist, Chris McKay, holds that the methane lakes on Titan contain creatures so unlike Earth creatures that they exceed our wildest imaginations.
Think of fish living in water and ask them to imagine a bird which lives in air. They probably can't conceive of an organism that is so much denser than the medium in which it lives. Fish move through water by floating. So they would imagine a bird must float in the air.
We humans live in an environment called Earth. We produce energy by causing oxygen and organic matter to interact. That is our lifestyle. But McKay is arguing that on Titan, life forms would be based on a Titan lifestyle that makes use of what's available on Titan. Titan's atmosphere contains minuscule amounts of hydrogen and acetylene. McKay thinks that there may be life forms on Titan that exist by deriving energy from the interaction of those two substances in a methane environment. McKay says that life could very well already exist on Titan.
So instead of being small and round, I would guess that a single-celled organism on Titan might be big and flat, like a sheet of paper, to maximize its contact with the nutrients in this thin soup. So it's living in an environment where there's not a lot of food. So it's got to access the food with big area. And maybe on this area, it has active molecules. So it's like a big flat sheet of paper with little traps on it to collect food. To that life form, that will be the normal environment.
It was not until the 21st century that Titan's thick veil was lifted. Now that we're getting a closer look, what new discoveries await?
So Titan gives us a whole new set of possibilities, and there are for sure perhaps hundreds, maybe millions of worlds like Titan around other stars. Do those have life? Titan maybe can give us some clues.
If life is found on Titan, humanity's view of the universe will surely change.
The best place for me in terms of finding another type of life would be Titan, because if we find it on Titan, then we know that it really is too. It's not the same as us. When we go to Mars, we may find life on Mars, but we won't be sure that it's not the same life as Earth. So my best hope would be we find life on Titan, because then I know that we found two completely different types of life. Then I can go on to some other science problem.
There is only one body in space that we know of, other than Earth, that has a thick atmosphere and lakes. Titan. If life is found on Titan, it will instantly increase the possibility that life exists in many other places in the universe as well. We may not be alone in the universe. We may have many comrades. The quest to find out for sure continues. Clues to solving that great mystery lie hidden on Titan. (1997) saw the launch of the Cassini-Huygens mission. The Cassini orbiter, equipped with cameras and other instruments, and carrying the Huygens probe, was sent to investigate Saturn and its moons, especially Titan. In 2004, 7 years after liftoff, Cassini-Huygens reached the vicinity of Saturn, 1.4 billion kilometers from the Sun. Cassini then proceeded to enter into orbit around the planet and its satellites, and to commence scientific observations. It took this image of Titan. For the first time, Titan's true features began to show from under that thick haze. The day was approaching when we would finally be able to see the surface of Saturn's giant moon. In December 2004, the Huygens probe separated from Cassini and coasted to Titan. The target landing site was near Titan's equator. What that site would be like, no one knew. Surface. Ralph Lorenz has dedicated himself to investigating this strange striped pattern. He is trying to solve the mystery of Titan's stripes by comparing them to patterns he finds on Earth. This is the Mojave Desert in the western United States. Lorenz believes Titan's stripes are like the peaks and troughs of desert sand dunes. There are indeed real similarities.
It's remarkable somehow that despite the different gravity, the thicker atmosphere, and the different material that the sand is made of, somehow the landscape ends up looking almost exactly the same as many places on Earth. By comparing the shape of the dune and the interaction with the rest of the environment, we can get an understanding of how these structures formed. And for example,
now from 8,000 meters above Titan, it looks just like the sort of coastline we're used to seeing on Earth. Finally, the landing. This is an image taken by Huygens just after landing. What look like rocks and pebbles strewn about over a flat plain are actually chunks of ice. The surface temperature is minus 180 degrees Celsius. Atmospheric pressure is a little higher than Earth's, 1.5 bars. The horizon seems blurred by mist. This is exactly like some rocky desert landscape on Earth. High above, the Cassini orbiter continued its observations. In the equatorial region where the Huygens probe landed, Cassini discovered a strange pattern. Some sort of regular striping. Further observations found similar striations covering some 20% of Titan's. Imagine the journey from Earth to Titan. If you could travel at the speed of light, you'd pass Mars about 4 minutes into the voyage. At the 30-minute mark or so, you would pass the giant ball of gases known as Jupiter. Then, some 70 minutes after departure, you would finally arrive at Saturn surrounded by those beautiful rings. Like Jupiter, Saturn is a large, gaseous planet. Finally, you'd reach Titan. With a diameter of 5,000 kilometers, Titan is about 3/4 the size of Mars. It's a moon the size of a planet. Fully cloaked in that orange haze, Titan's true appearance was not known until the 21st century. Titan's atmosphere is 1,000 kilometers thick. The probe entered it. Huygens deployed a parachute and drifted down, jettisoning its heat shield. This image, taken from a height of 152 kilometers, was Huygens' first view of Titan, which was still obstructed by haze. Huygens was shooting still images as it descended. Its microphone also captured the sound of the wind rushing by. This was the first sound recording ever made of an alien environment. These images of Titan's surface were taken by Huygens from 16,000 kilometers up. Black veins like the branchings of a river are visible. It does look as though they are flowing to the mouth of a river.